Welcome to this Discovering OpenSees webinar today. This webinar today is actually a continuation of an earlier webinar on hybrid simulation that we had last year. Today we're going to be talking about how we're going to conduct hybrid simulations with OpenSees and OpenFresco. What I'm going to show you guys today has a lot of slides, so I'm going to try to cover a lot of material today. So please bear with me, and I'm going to warn you right now that I'm probably going to go over time by about 10 to 15 minutes. So it'll be about an hour 10 to an hour 15, the whole seminar. So hopefully you can stay tuned in all the way till the end. But I think it is important to go a little bit over time and really cover all the material nicely that I'm going to show you here today. So welcome again to that. For the outline of the presentation today, I'm going to first give you a short introduction to hybrid simulation, just to bring you to the point that we are all aware exactly what hybrid simulation is. And from there we can then go into the OpenFresco architecture, so I'm going to show you that, and also the tickle commands, how we can use tickle commands similar to what we are doing in OpenSees inside OpenFresco to generate all the different objects. I have to say that everything that I'm going to show you today is based on that you have some knowledge of OpenSees already. So I'm going to rely on that. So it's not like a beginner's presentation, it's more like an intermediate to advanced presentation here. So I'm assuming that you know something about OpenSees. So I'm not going to go into that. Then on the third point, I will show you how to download and install OpenFresco. Then I'll go in detail through an example and show you how to set up a hybrid model using OpenSees and OpenFresco. Then I'll have a short few slides showing the difference between using simulated versus real controllers. So the example that I'm going to show you in number 4 is a simulated example, and in 5 I'll show you how you can switch that over very easily to do actually a real test with a real controller. Then in 6, I'll show you a few computational drivers that we can use besides OpenSees. So I have a few slides on that, and then I'll give you a summary and conclusion. So for the introduction to hybrid simulation. So what is hybrid simulation? First off, if we do experimental tests in a laboratory, we can typically do 3 types of tests. So you see the 3 columns that we have for the 3 types of tests that we can do in an experimental lab. The first column is quasi-static testing, and you can see what we can capture in the different rows. So for a quasi-static test, we can capture the dynamics. We say no, because typically we run it as a quasi-static test. So we'll do a slow test, and we're not capturing the dynamics. Strain rate effects, also, we cannot capture that with a quasi-static test, again, because we are running something slowly. And then for large or full-scale tests, that's very typically that we can do that with a quasi-static test, because typically we have large actuators in a laboratory and we apply load slowly, and so the only limit is really the size of the actuators and the reaction wall or reaction frame that we are using. So typically we can do very large-scale or full-scale tests with a quasi-static experiment. Then for the second column, the shaking table test, well, obviously we're testing there in real time, or sometimes even faster than real time if we consider similitude laws. So we capture the dynamics with a shake table test. We can also capture strain rate effects because we're testing in real time. But typically it's very difficult to do large or full-scale tests on a shake table, unless you're maybe somewhere in Japan on the E-Defense shake table where you have a very big table, and otherwise typically we are limited on how much weight we can put onto the table, how big the specimen, how heavy the specimen can be, and how hard we can shake it. Then finally, what we're focusing on today is hybrid simulation, the third testing method in the diagram here. And you can see in hybrid simulation we can capture the dynamics. Usually we capture that inside the numerical portion of the hybrid model. If we do a real-time hybrid simulation, we can actually also capture strain rate effects. So anything that is velocity dependent, as long as we can test in real time, we can capture that behavior. And because we're using actuators to impose displacements, Typically, we're just limited by, again, similar to the quasi-static test, by the size of our actuators that we have in a laboratory and our reaction frames, reaction walls, on how big a testament we can test. So if we have big actuators, we are not limited and we can go to very large scale or even full scale tests using hybrid simulation. If we do a hybrid simulation, well, typically we'll start off with a purely numerical simulation. So we have a 3-story zipper frame here, a full numerical model, and we would feed in a ground motion at the bottom of that structure, and we will shake it. If we do that, we shake it around, purely numerical simulation, not hybrid yet, we have the equations of motions that we need to solve. And inside that equation of motion, we have some inertia part, mass times acceleration, we have energy dissipation, typically some damping matrix times the velocity, and we have resistance, so some resisting forces that we are assembling from all our numerical elements. Now, if we do a hybrid simulation instead of a purely numerical simulation, we'll come along and we'll replace part of the structure, in this case the bottom story brace, we'll replace that with a test specimen. And so we will go into the laboratory and build some kind of experimental setup where we can test the brace. And typically we will attach to the brace, there you can see at the top a big loading frame, and we'll attach actuators so we can actually impose displacements, and we will have devices to measure forces. So you can see inside the hybrid simulation, all the blue parts in our model represent the analytical portions of the structure and the energy dissipation and the inertia, and then the white parts are the physical portions of the structure. And so you can see the mass times acceleration, our inertial effects, and our energy dissipation effects are modeled numerically. And our resisting forces are a combination of numerical portions from some elements, but also experimentally measured forces from the test specimen in the laboratory. On the right-hand side of our equations of motions, we have the dynamic loading. And typically we are dealing with seismic loading, but hybrid simulation is not limited just to seismic loading. We can also do wind loads, blast impact loads, wave loads, or even traffic loads if we like to. Other loads that we can put on are static loads. So before we actually run the dynamic load or the dynamic analysis, we can put on static loads. So we can put on gravity loads, or if we like, pre-stress loads. And this is important. I will show you in the example later in today's presentation how this becomes important and how we can do that. Another nice thing that we can do in a hybrid simulation is whatever the forces are that we're measuring in the laboratory, we can analytically add nonlinear geometric effects to the measured resisting forces, and by that we can then capture second-order effects numerically. And again, I'll show you how that is done in the example later in the presentation. So in a hybrid simulation, what we typically then do is we model the well-understood parts of the structure in a finite element program, and we can do this on one or more computers. So we can, if we want to run this on a supercomputer machine, we can take care and access multiple machines and run it on multiple computers if we like to. Then we leave the construction and the testing of the highly nonlinear portions of the structure, or the portions of the structure that we don't know so well how to model numerically. We basically leave those in the laboratory. So we build a specimen in the laboratory to test that part. And again, we can use one or more laboratories. So if we want to take up resources from different laboratories and take advantage of different resources that different labs might have, we can do that across multiple laboratories. So typically then we can consider a hybrid simulation as a conventional finite element analysis where the physical models of some portion of the structure are embedded in the numerical model. If we look at the components that we will need to do a hybrid simulation, well, first off, we need a discrete model of the structure that we want to analyze. And that discrete model should include any static or dynamic load. Then we need also in the laboratory some servo-hydraulic control system with static or dynamic actuators depending on how fast we are trying to run this hybrid simulation. So we have a control system and the actuators, and the control system will tell the actuators how to move. Then obviously we need the physical test specimen itself. So whatever we are not modeling numerically, we'll build it in the laboratory and have that test specimen. And because we're trying to impose displacements, really forces onto the specimen, we will have to obviously have some reaction wall that we can react against with our actuators, so a reaction wall or reaction frame. Then finally, we want to take measurements while we do the hybrid simulation, so we'll need a data acquisition system with instrumentation, so with load cells, with displacement transducers, so we can measure forces and displacements as we go along and do the hybrid simulation. For the testing methods, there's several different testing methods that we can do with hybrid simulation. When people started off doing hybrid simulation, they did a conventional hybrid simulation test where the specimen was loaded using a ramp and hold loading procedure. So you would ramp up to a certain target displacement, and then while you take your force measurements and while you compute the next target displacement, your actuators would hold the position. Now this had usually the problem that during this hold phase, forces in your specimen would relax. So to alleviate that, people then developed what is called a continuous test, where the specimen is loaded at a continuously slow to moderately slow rate, which then, if we continuously move the actuators and we never stop, we can avoid these load relaxation problems. Then this still doesn't capture strain rate effects or velocity-dependent behaviors. So then people took a step further and they said, well, let's try to do a real-time hybrid simulation where we test the specimen at a correct velocity to account for rate-dependent material behavior, so we can capture the rate effects. And then finally, as I said, if we want to take the advantage of multiple laboratories, having like different resources at many different laboratories, we can also geographically distribute a hybrid simulation across a network and communicate between different laboratories and different numerical sites. So now let's talk about the OpenFresco software framework. OpenFresco, what does it stand for? It stands for Open Source Framework for Experimental Setup and Control. And it is a secure, object-oriented, network-enabled middleware. So it's a middleware, and that's a very important point. A middleware means that it pairs computer analysis software with laboratory control systems and other software to enable hybrid simulation. So OpenFresco by itself cannot do hybrid simulation. So you will need some computational drivers, and you can see what we have in terms of computational drivers. So you'll need, for example, here today we're talking about OpenSees. So you need a computational driver, and then OpenFresco as a middleware will allow you to connect your finite element software to the laboratory control systems. In terms of computational drivers, we have OpenSees, we have OpenFresco Express, which is a graphical user interface that I was showing in an earlier presentation about this same topic a year ago or so, a little less. Then we have Abacus. We can use that to do a hybrid simulation. We have an LS-Dyno implementation. We have MATLAB. So if you like to program your finite element analysis in MATLAB, you can do that. We have Simulink. So we have certain blocks that you can drop into Simulink to connect to OpenFresco. We are almost there having an implementation for ANSYS, so that should come out soon. And then we have UI SimCore, so we can talk to that too. For the control systems on the right-hand side, we can talk to DSpace. We can talk to several MTS controllers. We have the SDS family. We can talk to FlexTest through the CSI software, or we can talk to FlexTest through ScramNet. We also have an implementation for National Instruments controllers. And we can talk to Pacific Instruments data acquisition systems, and we can also talk to AD-Win controllers. So you might ask yourself, why do we need a software framework? Well, in the past there was a lack of a common framework for the development and also the deployment of hybrid simulations. And so in the past, problem-specific implementations were very site and control system dependent. So everybody would come along and implement it just for their laboratory, whatever controller they had in their laboratory, for whatever specific problem they were looking at. And if then somebody else came along, it was very difficult to adapt these problems or these implementations to new problems. And that's really why we need this software framework, OpenFresco. And it provides a robust, transparent, adaptable, and easily extensible software framework that we can use for research and deployment. If we rethink on how we implement the strategies, what approach did we take when we developed OpenFresco? Well, we said, let's take the finite element approach where we look at a hybrid simulation as if it was a finite element analysis. But because we do a finite element analysis, we want to replace certain numerical elements with experimental elements. And if we do a finite element analysis, typically, if you have any finite element software, whatever your favorite one is, they will all have similar things. They will have to define nodal geometries. They will have to define boundary conditions. You'll have to put on some mass and damping properties on your structure. You'll have to set up loads. And then very importantly, you'll have to set up your elements. What are the different elements that represent the different portions of your structure? And so you go ahead and you select from your favorite finite element software some numerical element that you know it's working well and you can capture behavior really nicely. So you model some portion of your structure using numerical element number 1. For another part of the structure, you might use a different numerical element number 2. But then for the third part of the structure, you don't really have a good element inside your finite element software. So there's nothing there that you feel confident that can model the behavior correctly. So what you do is you basically define that third portion as an experimental element. And you define that experimental element, you build it in the laboratory, connect it to some controllers and data acquisition systems in your laboratory. So now the task is how do we talk from our finite element software to our laboratory, and that's where OpenFresco comes in. And it will allow you to send out response quantities, typically displacements, through OpenFresco to the laboratory. And then typically we measure forces in the laboratory, and we can send forces back through OpenFresco into our finite element analysis software. There's some questions coming in. I will answer all the questions at the end of the presentation. So if we look at the OpenFresco components, like I said, at the very top we have the finite element software, and that should be any software you like that you want to use. You don't need to modify it, just use that computational framework. So you like to connect to that. At the very bottom we have our control system in the laboratory, which has some actuators. We have the controllers, we have the data acquisition systems with all the physical instrumentation devices. So we need to be able to talk to that. So that's where OpenFresco comes in, and you can see there's 4 main objects inside OpenFresco. So they're abstractions of real things in the real world. So the first object is an experimental element, and that really represents the part of the structure that is physically tested and provides the interface between the finite element software and the experimental software framework. So that's the experimental element. Then next, from the experimental element, we go one step down and we go to the experimental site object. So that experimental site object stores data and provides communication methods if we try to do a distributed test. So we can do either a local test or a distributed test across the network. That's where the experimental site distributes things across the network. The third object represents or is an abstraction of your experimental setup that you will have to have in the laboratory. So this is the software abstraction. And what it does, it transforms between the experimental element degrees of freedom and the actuator degrees of freedom. And these transformations can be implemented as linear or nonlinear transformations. Then finally, our last object is the experimental control object. And that one really interfaces with the controller and data acquisition systems in the laboratories. Some other requirements that came along while we were developing OpenFresco were that we want to provide connectivity to a wide variety of finite element software clients. And that should be independent of the language that these clients are written in. So some finite element programs are written in C++, like OpenSees. Other ones will be programmed in Fortran or BASIC. And we want to be able to talk to all of them independent of what language they're in. So that's one additional requirement. We also want to enable distributed testing and support different communication protocols across the network. And then finally, we want to interface with a rapidly evolving control and data acquisition systems in the laboratory. And each laboratory all over the world, everybody is using different data acquisition systems, different control systems. We would like to interface with all of them. So with these additional requirements, we then decided to wrap around the main 4 objects in OpenFresco what is called a multi-tier software architecture. And with that, we can then deploy OpenFresco in many different ways. So this first slide here is showing how we can deploy locally. And you can see there's 3 figures. Let's start with the one on the very left. So on the left, we have our finite element software of whatever that is, your favorite finite element software that you choose, and we will implement inside that what we call a generic client element. So generic client element is just defining what nodes your element connects to and what degrees of freedom you use. It doesn't really tell you, is it a beam column element, is it a wall element, is it a truss element? You don't know, it's just generic. And that's why we have an experimental element then on the middle tier server side inside OpenFresco. So all the green parts are the OpenFresco parts. So here's the experimental element. Another way to do this is the middle column. Some people might say, well, I really want to take advantage of some features in my finite element software and implement directly an experimental element into the software. Instead of a generic element, I want an experimental element. So I will directly implement my beam column element. If we do that, then obviously in OpenFresco, in the middle tier server side, we no longer need to define the experimental element. So you can see that that is missing there. So we can do that as well. Then finally, the third column, and that's the most important, at least for today, is if we want to use OpenSees. Because OpenSees and OpenFresco are both developed in C++ with an object-oriented approach, we can actually take advantage of communicating between the two using function calls. In these other 2 implementations on the left, we will have to use TCP/IP connections to talk from the finite element software to OpenFresco. But if we use OpenSees, we can use function calls so we can run things faster. And it becomes a little bit easier. So we'll directly have access to our experimental elements from OpenSees. If we look at the network deployment, it's very similar. So the 3 columns are the same thing. On the left, you have the one where we implement a generic client element into the finite element software, middle one where we do the experimental element, and then the right one is OpenSees. The difference is that now we break this up across a TCP/IP channel between a client and the middle tier server, and this is really the network. So you would have the top portion here being in one laboratory and the bottom portion being in another laboratory. So that's how we can start doing distributed tests. So we'll break it up. So that's the network deployment. If we now look for each object of the 4 main objects in OpenFresco, a little bit in more detail what we do inside those objects. So let's start off with the experimental element. You can see that experimental element transforms between the global element degrees of freedom in the finite element software and the basic element degrees of freedom in the experimental element. So if we take this portal frame like I showed there, and we take the inclined member out, and we want to make this an experimental portion of our structure, we would take this out, and because it's a 2D problem, so we have a beam column element in 2D in our global system, we will have 6 degrees of freedom. So we will have 4 translations and 2 rotations. So these 6 degrees of freedom, we will reduce that, taking off the rigid body modes from our global system and convert it into a basic system without rigid body modes, just the deformations. And typically there is 2 different basic systems that we can choose. OpenSees usually is choosing not the one I'm showing here, but is using the simply supported basic system, where we have 1 axial degree of freedom and a rotation at node I and a rotation at node J. So that's what OpenSees will do. Now for a laboratory test, rotations are a lot harder to impose than translations. And so we chose to go with the basic system, the cantilever basic system, instead of the simply supported basic system, because at least for that one we have 2 translations and only 1 rotation. So it makes it a little bit easier to impose the displacements than the rotation. So that's the experimental element. Then for the experimental site, like I said, it provides communication methods to do distributed tests. It also stores data while the test is going on. And the communication usually happens across a channel, and the channel can use different communication protocols. So you can use TCP/IP. If you are worried about security, you can use TCP/IP with secure socket layer, so you can encrypt all the data that is being sent across the network. Or if you do something more locally and don't send stuff very far, you might want to use UDP. UDP has the disadvantage that there's no guarantee that whatever you send out gets to the other site, but it has the advantage that it runs a lot faster. So it has advantages and disadvantages. So with that, we can then test between different sites. Are they numerical sites or experimental sites? It doesn't matter. Different sites all over the world. Then for the experimental setup, to reiterate one more time, that one transforms between the basic experimental element degrees of freedom that we were doing in the experimental element object, and transforming those degrees of freedom into actuator degrees of freedom in your laboratory. And again, these transformations you can do as linear or nonlinear transformations. So if we go back to our inclined experimental element that we looked at in the experimental element object, again, in the cantilever basic system, now we have these 3 degrees of freedom, 2 translations and 1 rotation at node J. Somehow we need to impose those in the laboratory. There's different ways to do that. One way would be that we take our specimen and we attach a big loading frame on top of it and have 2 vertical actuators and 1 horizontal actuator attached to this. And with these we can then impose the 2 displacement and 1 rotation at the top of the column. If we do this transformation from the basic element degrees of freedom into our actuator degrees of freedom as a linear transformation, this is very simple and can just be written in terms of this transformation matrix that I'm showing there. If we want to do this transformation for large displacements, so take into account nonlinear geometric effects, then that becomes a lot more complicated, and I'm not showing that. Finally, the experimental control. There's different ways to do this. Just showing one implementation that we have where we can talk to different MTS controllers across D-space. Across XPC target. So we can have XPC target, which is a digital signal processor, and on this we will run a Simulink model, which from that Simulink model we will then communicate to the MTS controller. So that's one implementation that we have for the experimental control. So now, short few slides on the OpenFresco tickle commands. The tickle commands, the approach we're taking with OpenFresco is very similar to what is in OpenSees. So for any object that we need to create, we added new commands into the tickle interpreter. The first one, or the first example that I'm showing here, is for a beam column element. So this is an experimental beam column element. So instead of saying element, we will say experimental element. We'll tell what the type is, a beam column. Then we will give it a tag, the same thing as OpenSees. Everything has a tag. We'll tell the connectivity, so it's connecting from node I to node J. So up to here, and then, well, even the next one too, the transformation tag. So there we will tell it, because it is a frame element, we will tell it how we're transforming between global degrees of freedom and our basic degrees of freedom that I was showing you, how we have to take off the rigid body modes and do this transformation. We will actually use the coordinate transformations that are available in OpenSees, so we can do a linear transformation, a p delta, or co-rotational transformation. So we'll have to specify what we are using there. So up to that point here, it's all the same as if we were doing a numerical element in OpenSees. Now, the new arguments that we have to specify, because it's an experimental element, is at what site is this at? And so we will define a site, and then previously defined tag, we'll use that here, what site it is. And then because it is an experimental element, and typically it's quite tricky to figure out what the tangent stiffness matrix is from just measurements in the laboratory. So what we typically do for an experimental element is use an initial stiffness matrix instead of a tangent stiffness matrix. And so we will have to provide all the different components of this initial stiffness matrix. And that can be determined through analysis, so you can analytically determine these stiffness components before you do the test, or you can go into the laboratory and impose small displacements on your specimen, measure forces, and calculate your stiffness from that. So different ways to do that, but we need to provide that initial stiffness matrix. Then the next thing is the experimental site. So that's a very easy command, at least when you do a local experimental site. So you're just testing at one location. You're not distributing stuff across the network. Then what you would do, you would say experimental site. The type would be a local site. You'll give it a tag, and you will tell it what setup, what experimental setup you're using. The experimental setup then, I'm going to go back to the one I showed you before, which is a 3-actuator experimental setup. So you will tell experimental setup, tell the type, which is 3 actuators, give it a tag, specify what controller you will be using, which controller are you talking to in the laboratory, and then you will have to provide some geometric quantities that are important because we are trying to do maybe a nonlinear transformation. So you will have to tell it what are the initial actuator lengths of your 3 actuators, and you will have to tell it what are the different distances of your rigid loading beam on top. And so all these arguments need to go in case you are doing a nonlinear transformation. Then finally we have an argument here which tells you what the position of your actuator 1 is, because that can be placed on the left or on the right, and the transformations will change depending on that. And then also what the relationship is of your loading beam with respect to your local coordinate system of your element. So that will be the phi local x. So you'll tell it, in this case right now, our local degree of freedom of our beam or column element really is in vertical direction, so along the axis, and so that one has an angle of 90 degrees with respect to your loading frame, so you'll put that in. And then finally you have some other optional arguments that are allowing you to modify quantities that you're sending out to the laboratories, and also quantities that you're getting back from the laboratory. You can put factors onto them, and you can do that inside the experimental setup. And that's really important in case you want to take care of similitude laws and account for things like that. So then you can modify your signals that you're basically sending out and getting back by certain factors. And I'll show you a little bit more in detail how to do that. Then finally we have the experimental control, showing again the XPC target. So what we do is we'll say experimental control, the type would be XPC target, we give it a tag. The type of the predictor corrector model, which is the Simulink model, we will have to specify that. And then also we'll tell it what is the IP address and the IP port of our XPC target machine, so we can actually access it across the Ethernet. And we'll have to tell it what is our application that we are trying to run on the XPC target, so that will be a Simulink model. So we'll give it the name of that Simulink model and the path of where it is stored on our machine. So that's how you set up an experimental control for XPC target. All these commands are actually described in the command language manual and many more. I only showed you one example for each object, but we have a lot of other ones. So they're all there in the OpenFresco command language manual. And so you can go onto the OpenFresco website, go under documentation, and download the OpenFresco command language manual, and it will show you all the different commands and what it means. So now let me show you how to download and install OpenFresco. So first you will go to the OpenFresco website, which is under openfresco.berkeley.edu. You will then come over to the tab called User and go down to OpenFresco. And if you click on that, it takes you to the OpenFresco site. The first thing you will have to do, either if you have an account already, you will have to log in, or if you don't have an account, then you can actually register for one. So you have to do that first. And then you scroll to the bottom of the page, which will look like that. And at the bottom of the page, you will first, basically just follow the 4 steps that are lined out there. So you'll first have to download and install Tickle. I'm assuming, since we're talking about an OpenSees seminar here, that you already have Tickle TK installed, because you need that for OpenSees as well. So, but if you haven't, download it and install Tickle TK, and if you do that, it is very important that you install it in under C program files Tickle, which is not the default location where it wants to be installed, so make sure you change it to that location. Otherwise, both OpenSees and OpenFresco will not find Tickle. Then optionally, if you want to do encrypted communications across the internet, then you do need OpenSSL, which stands for Open Secure Socket Layer. So you'll have to download and install that as well, and so you just have to follow step 2 there. If you're not worried about that and you don't want to use OpenSSL, then you don't need to do that. So that's why it's an optional step. Then third step, you need some computational driver, and today we're talking about OpenSees, so you'll have to install OpenSees, and again, I'm assuming you already have that. If you don't, go to the OpenSees website, follow the procedure there on how to download and install OpenSees. If you use some other computational driver, then you would have to install those, Abacus, LSDyne, or whatever you're using. Then finally, you are ready to download and extract OpenFresco. So all it is really a zip file, and so you'll download that zip file and extract it in any convenient directory where you would like to have it located. I put this in some directory here just to show you today, and if you do extract it, what you will get is a bunch of files. The most important one is the openfresco.exe, so that's the executable. Second most important one is right above it. That's the OpenFresco DLL, so Dynamic Link Library. That one is important. That one will be called from OpenSees. So if you use OpenFresco together with OpenSees, then OpenSees will actually access all the OpenFresco commands through this Dynamic Link Library. All the other dynamic link libraries that you will get have to do with the different experimental controllers that OpenFresco can talk to. So these are different interfaces to talk to different controllers. At the very bottom you can see, for example, the one that we use for XPC to talk to XPC target. So then you want to make sure it's running correctly. So what you want to do is in whatever directory you placed all these files, you want to start a DOS command prompt in that directory. And I advise you to start a DOS command prompt and not double-click on the OpenFresco executable. It's a much better procedure to start a DOS command prompt, type in OpenFresco, and hit Enter, and then that should just run it. The reason that you want to open a DOS command prompt first and not just double click on OpenFresco. And by the way, that's the same that applies for OpenSees too. It's always better to open a DOS command prompt and then type OpenSees versus double clicking on OpenSees. And the reason is that if anything goes wrong, if anything is wrong with your installation or anything is wrong with your input files and the software crashes, it will show you what the error is. If you just double click on the executable, then whenever an error happens or occurs, then the window just gets closed and you will not see what the error message is. That's why I advise everybody to always use a DOS command prompt and then start it from in there. If you're a developer and you want to get the whole source code, not just the executable, then you can go on the OpenFresco website, go to developers, and there is an SVN tab there. And so similar to OpenSees, you can access the whole source code and download everything through SVN. I typically use Tortoise SVN on the Windows systems, a very nice application. You can access the repository and always get the very latest code as we develop things. So now let's look at the example. So how do we build a hybrid model using OpenSees and OpenFresco? And first off, what I would like to show you here, the example that we're going to look at is how to do a hybrid simulation of structural collapse. To give you a little bit of motivation why we want to do a structural collapse, well, you can see the bridge here that completely collapsed in the Kobe earthquake, or this concrete parking structure during the Northridge earthquake that totally fell over and collapsed onto its side. So structural collapse is important to look at. If we do structural collapse on a shake table, because that might be the first thought, if we want to test something, let's do a shake table test and let's do structural collapse, that can be very dangerous and expensive. And you don't want to have the structure collapse onto your table, damage instrumentation devices, or you will have to install some very expensive system to hold the specimen in place once it does start collapsing. So it's tricky to do collapse simulations on a shake table. However, if we do it in hybrid simulation, it becomes fairly easy. So we can apply gravity loads and also the resulting geometric nonlinearities all analytically in the model. So instead of doing it in the experiment, we will put it in the analytical portion of the model. And because we do that, we don't need any complex active or passive gravity load setups. Also, the actuators that we're using to impose displacements, we can set limits on those. And we can say, well, if we move that much, that constitutes collapse, and we can stop our actuators at that point. And so again, we don't need any expensive protective equipment to prevent the specimen from impacting once it starts falling over. So we can control that with our actuators by setting displacement limits. And then finally, we only need to model the collapse-sensitive elements physically, and the whole rest of the structure we'll put into our numerical portion of the hybrid model. So again, basically what I just said, in the physical portion of the model, we test the material and cross-section level response, and in our analytical portion of the model, we apply the gravity load and or pre-stress loads. We also provide the geometric transformations such that we can capture the second-order effects due to the axial loads that are on our element, and we model the rest of the structure that we are not testing. So this example that I'm going to show you is a portal frame. So we're going to do structural collapse of a portal frame. You can see the portal frame model, it has 8 degrees of freedom, so it's actually pinned at the bottom here. And 4 of these degrees of freedom have mass on them, the other 4 don't. The fundamental period, first mode period of the structure is close to half a second. We will put some damping on there, 5%, and we put gravity loads on node 3 and node 4 at the top that correspond to 50% of the capacity of the 2 columns. And then when we do the test, we can do the coordinate transformation because these are frame elements. We can do that in terms of a p-delta coordinate transformation or a corotational transformation. So we can choose one or the other. The experimental elements that we're going to use are beam column elements. The setup you can see from the picture above. So we have 2 1 actuator setups that connect to the columns. We will use XPC target in this case. Well, today actually we'll use a simulated one because in this presentation I cannot show you a real one. But for the real test that we did when we first did in the Berkeley laboratory here, we were using XPC target to talk to these actuators in the laboratory. And then finally we'll put a ground motion on there, which is the SAC NF01 motion, which is the Tabas earthquake, and it's scaled to a PGA of 0.9 Gs. If we look at that architecture again and just quickly remind ourselves what the different portions are, so we will have our beam column element defined inside OpenSees, so the experimental element will be sitting directly in OpenSees. We'll use a local site because we're doing a local test, so we are not distributing things. We'll have the transformation between the experimental element degrees of freedom and the actuator degrees of freedom done in terms of a 1 actuator experimental setup. And the experimental control, we will use a controller which is called Sim Uniaxial Materials that allows you to simulate the behavior of the controller using any uniaxial material that is available in OpenSees. So by simulating everything, we don't have a real controller in the laboratory, but we use a material to simulate stuff. So let's go through the Tickle script and look at the different components. So let's start off with the geometry. How do we define the geometry? So this portal frame model is a 2D model. So we will set up a model builder. and these are now OpenSees commands, so there's not OpenFresco yet. So this is an OpenSees command, set up the basic model builder, which has 2 dimensions, so NDM is 2, and each node has 3 degrees of freedom, 2 translations and 1 rotation, so NDF is 3. The second command, which is very important here, which is on line 28, is now we want to load into OpenSees all the OpenFresco commands, so that the OpenFresco commands will be accessible to OpenSees. And the way we do this, we basically state the command load package OpenFresco. So that will load in or will make accessible all the OpenFresco commands to OpenSees. Once we have that, we can go ahead and put in our geometry with all the nodes, and we'll put on masses. We'll just put the translational mass, no mass moments of inertia, those will be at 0. We'll put our boundary conditions. Again, we are pinning the structure at the bottom here. This becomes important, I'll show you later why. And we will have some flag set up with gravity or without gravity. If that flag is 0, that turns the gravity loads off. So we'll not capture any second order effects because we have no axial loads on the structure. And then with gravity, if we turn it on, then we can capture the second order effects, and we will see, we can run the example with gravity loads and without gravity loads and look at what the difference is in terms of the response. Finally, because I pointed it out, we don't have any rotational masses assigned. So because of that, we need to remember later when we do set up our analysis options that we must use an implicit integration method, because we have some degrees of freedom that have no mass on them. So then we go ahead and we start setting up the materials and the experimental control. For the materials, we want to basically, as I said, we want to use any uniaxial material to simulate our controller. So we'll first define that uniaxial material. In this case, I'm going to use a steel 02 material, which is a Menegotto Pinto material, which gives us a nice hysteresis loop. So we'll set that up, and then we'll come along and define our first OpenFresco object, which is the experimental control. So we'll say experimental control, sim uniaxial materials, give it a tag, and then tell it which material we want to use to do the control. And so this one would be the material 1, which is the steel 02 that we have defined above. And we do this twice. So we do it on line 57 for the column on the left, column 1, and we do it again on line 58 for the second column on the right. So 2 experimental controls. Then next thing to do is the experimental setup and the experimental site. So we have to define those. As I said, the experimental setup is a 1 actuator setup. So for each column, again, we'll do it twice. We'll come along and we'll set the experimental setup to the 1 actuator setup. We'll give it a tag. We'll tell it what control are we using. So this will refer back to the experimental control that we just set up on the previous page. So we'll have the experimental control 1 and 2. And then the next thing will be the direction. Which direction is this 1 actuator actually pushing? So as you can see, our specimen here, the experimental element that we have of this column, remember that this has 3 degrees of freedom at the end. So this is in the basic system. So the 3 degrees of freedom are the axial degree of freedom, the transverse shear degree of freedom, and then the rotation at the end of the cantilever there. So we need to tell it which direction is our actuator pushing, and that's that direction command. So we're pushing in the shear direction, which is direction 2, so we'll have to put there a 2. And finally, we need to tell it what the size is of the data that we are sending out and that we are getting back. And because we're using this experimental element, the beam column element, that has 3 basic degrees of freedom, so the element is trying to send 3 trial displacements, well, 2 trial displacements, 1 trial rotation to this experimental setup. So we need to tell the experimental setup that we are expecting 3 values from the experimental element. So that's the first 3. What are the trial values that we're sending out? Now when we come back and we measure stuff, we'll measure different things, and so we need to send three forces, well, two forces and one moment, back to our experimental element. So that's the output. So again, that will be 3 as well. So size trial out, they're both 3 and 3. Then we have the next thing that we can do is the optional arguments that we have in the experimental setup. I mentioned those before. If we would like to modify anything that we are sending out, so these would be the control values, so we can modify these. So if we want to modify for example, the displacements that we're trying to send out, then we could say, and as an optional input, control displacement factor equals 2. So that would then take your target displacement, the control displacement, and multiply it by 2 before it sends it to the controller. So this is important if we try to take similitude laws into account, or if we typically just want to maybe send out a bigger displacement than what we are actually calculating. And then we can do the same thing with all the measurements that we're taking. So these will be the DAC values, anything that we measure, displacement forces and so on. We can modify those too. And so if we, for example, if we send out twice the displacement, we should probably take half the displacements of what we measure when we send it back. So we would say DAC displacement factor is a half. So every one of these factors will always multiply whatever your response quantity is by the factor. So then next thing would be the experimental site. So we have to define that. This is a local test, so it becomes very easy. So it's experimental site, local site, give it a tag, and tell it which experimental setup you're using, which would be the two that we have defined above on line 64 and 65. Once we have that, we can go ahead and define geometric transformation, the experimental element and the numerical elements in our structure. So the geometric transformation, this is now very important because we're trying to do structural collapse. So we can either use p-delta transformation or corotational transformation. In this case here, we're using the corotational transformation. Then we come along and we have to define our beam column elements themselves. So give them a tag, and then the next thing would be the connectivity, going from node I to node J. Now this is very important here. Let's see. You're defining the connectivity, as you can see, from 3 to 1. So actually on the left, we're going from node 3, which is the top node, to node 1, which is at the bottom. The reason I'm doing that, or if you look at this, what this really does is flip our specimen in the lab kind of upside down, right? So because we're saying it's going from top to bottom, so it's going this direction. The reason I'm doing this is because I'm only using one actuator at the end of the specimen. So I'm only controlling the translational degree of freedom. Rotations, meaning will be something, but moments will be 0 because I'm not doing anything there. So the moments at the bottom will be 0, and you can see that corresponds exactly what we have in this portal frame example, where the bottom portion at node 1 and at node 2, they're both pinned, so no moments there. And that's why we're defining it this direction. So that's important. And then the next thing we will say what the site is that we have previously defined. And then finally we'll have to define the initial stiffness. As I said before, every experimental element is using initial stiffness that we need to provide. And so typically for that type of element that we have here, the beam column element, it has 3 degrees of freedom. So it will be a 3 by 3 matrix, and you can see what the different terms are. So we can calculate those if we know what the length is of the element, we know what the area is, moment of inertia, and the E modulus, and then we can calculate all these different portions and basically figure out what these 9 values are and provide them inside the initial stiffness command there at the end of the experimental element command. And then finally we have the numerical element at the very bottom here. So we have another elastic beam column element. So this is now a typical OpenSees element to model the top portion of our portal frame. Now we have the geometry and everything set up. Now let's define the loads and actually do an analysis. So first we'll put on gravity loads. So gravity loads are put on nodes 3 and 4 in the negative y direction. So vertically down, we'll put on our gravity load that we had defined at the very beginning of our tickle script. Once we have that, we want to run the gravity analysis. And to do that, we need to define analysis option to do the gravity load analysis. And so we can step through this. These are all, again, now OpenSees commands. So we'll have to tell it what the system of equation is. So we're using a band general system for this type of application here, this very small problem. Then for the numberer, how we're going to number our degrees of freedom, we'll use a plain numberer, so we'll use whatever our arbitrary numbering is, which for small problems, that's fine. For bigger problems, that would be too slow, but for this type of really small problem that we're doing here, this does not make a difference, so we can use a plain number. Then for the constraint handler, because we only have homogeneous single point constraints, no multi-point constraints, we're not imposing any support settlements or anything like that, everything is homogeneous, we can actually use a plain constraint handler. Then to test if we have convergence, we use an energy increment test with a norm of 1 to the e-6 and a maximum number of 10 iterations. Then for load control, for integration, how do we do the integration? Well, we use load control, and we'll do 10 steps here. So we'll do an analysis with 10 steps. And then finally, to do the solution algorithm, we'll use a Newton-Raphson algorithm to iterate as we go along. And then obviously this is a static analysis, so we'll give the analysis command as static. We will also define some recorders, so just so we know what is going on the nodes in terms of displacements and what is going on inside the elements in terms of forces. And then we can go along, and on line 142 we can analyze the structure for our 10 steps there and apply the gravity. So we'll ramp up the gravity loads over 10 steps to our maximum value, which is 50% of the capacity of the column. Once we have the gravity loads on there, we want to set up the dynamic loads and perform the dynamic analysis. So the first thing is we have to define where is our ground motion file. So we will use the ground motion, the ground accelerations, we will use that from a file. So we'll specify a time series, which is a type path, and we'll tell it where the file is. And again, as I said, this SAC NF01 ground motion that we are using here is the Tabas earthquake. Then we will apply the pattern, uniform excitation, so this OpenSees command, same as always, and we'll put on some damping here, some Rayleigh damping, well actually mass proportional damping here, our 5% mass proportional damping, so we put that on. For the dynamic analysis options, so we have to set those up. The first portion, system of equation, DOF number, and constraint handlers are all the same as in the gravity analysis. But then we need to start modifying things. So we're going to try to do, for the integration, I pointed this out at the beginning, we have some degrees of freedom that have no mass on them. So we need to use an implicit integration method. And what I would like to use here is what is called a Newmark hybrid simulation method with a fixed number of iterations. The way we specify what that fixed number of iterations is through the test. So the test, we are using a special test called fixed num iter, and we'll tell it we always, for each time step, we want to do 5 iterations, no matter what. So that's how you define that. And then for the Newmark method itself, you will have to, same way as in the typical Newmark method, which is not specific for hybrid simulation, the regular one, you'll have to provide 2 factors, which is gamma and beta. So we're putting gamma at 0.5, which makes this method second order accurate and does not put any numerical damping into our solution. And we will set beta at a quarter, which is equivalent to the average acceleration method, which is unconditionally stable. So those are the choices we make. Then the algorithm stays Newton-Raphson, and we switch the analysis to transient. Again, we will set up some recorders to record what's going on the nodes. We will add to the displacements also velocity, accelerations, and support or the force, nodal forces. And then for the element, we will record, again, all the forces inside the element. And what is new here, we will add some experimental recorders. So similarly to the recorders that you have in OpenSees, you have experimental recorders in OpenFresco, so you can record anything on any of the OpenFresco objects. So if we want to record what's happening on the experimental control, we will say experimental recorder for the control, and what are we recording? Same as in OpenSees, you'll see it, what it is at the very end. We're recording control displacements, data acquisition displacements, and data acquisition forces. Now that we have everything set up, we can run the dynamic analysis. So we'll first do an eigenvalue analysis, so we know what our eigenvalues are and our mode shapes, and then we'll go along and run our dynamic analysis, which is 2,500 steps, and we'll do that. If you do actually want to run this example, I forgot to mention that, but on the OpenSees website, excuse me, take something to drink here. On the OpenSees website, this example is available, so you can download it there, and also the presentation. I forgot to mention that at the beginning, I apologize. But if you do want to run that, what you do is start up OpenSees, the executable, in the directory where you have your example saved, and then remember again, don't just double-click on OpenSees, but actually open up a command prompt and then type OpenSees inside that command prompt, start OpenSees in that way, then source in your portal frame example and hit enter to run that. And when you do that, it will run the example, and you see we'll get a couple of warnings here, which are typical, so don't worry about those. They are just there because we are doing an eigenvalue analysis here, so which would require the element to provide the tension stiffness matrix. So again, as I said, our experimental element cannot provide the tension stiffness matrix, but will instead provide an initial stiffness matrix. So this warning is very typical, and you'll always see that. It's just to remind you. And then it will put out what the different periods are and frequency and how long the test took. Once we have that, we want to go in and see what our output is from all of our recorders. So in your directory where you have your example, you will now have a lot of output files from all your recorders. And with the example, I also provided a MATLAB file called plotoutput.m, which you can then use to basically post-process the output from all these different files. And if you do that, we can generate different graphs. So we can first look at deformations. How do deformations compare? And I ran this example now twice, once with gravity loads and once without gravity loads. So the one without the gravity loads would be the blue line, so you can see that. And once we put gravity loads on and we start capturing the second order effects, you can see how the example actually starts collapsing. So around somewhere between 6 and 7 seconds here, deformations get really big in the case where we have the gravity loads on our portal frame, and through each cycle they tend to get bigger, so really that is actually collapsing there. If we look at hysteresis loops, the top two figures are the hysteresis loops without the gravity loads. So the left would be the left column, right the right column. At the bottom we have the hysteresis loops with the gravity loads. Again, left would be the left column, on the right would be the right column. And the two colored lines in each of those plots is the red line is what we basically measure in the basic system. So this is exactly what we measure from our laboratory. So this is before we impose the second order effects numerically. So you will see that for the red lines, we tend not to see that the second order effect, which makes the stiffness negative, where we have this negative slope. So all the red lines still have the positive slope. And then once we superimpose numerically the second order effects, that will bring us into the global system. So if we look at those lines, the blue lines, you can now see how we can actually capture that second order effect and the negative stiffness in our hysteresis loop very nicely. So this was for how we simulate a control. Now if we want to do a real controller instead, I have very few slides on that. Basically the top portion stays the same, our model stays the same, OpenFresco stays the same there. But now we would like to talk, for example, to an MTS 493 real-time controller. and we will talk to that controller through XPC target, and through inside XPC target we will have a Simulink model. And so really what we need to do, we need to be able to talk from OpenFresco to XPC target, and XPC target in turn will then talk to the MTS controller that will send commands to the physical specimen or the actuators in the laboratory. So to switch from simulation to a real controller, all we will have to do is we'll go onto where we go back into our TICL file where we define our experimental control, and we will comment the experimental control sim uniaxial material command for, let's say, we want to switch the left column. So we will comment that out, and instead we will put in a new experimental control command for XPC target, which again has the IP address of your XPC target machine and the port, and it will tell it what Simulink model you're running on the XPC target. So that's fairly easy. So all you need to do is switch out the line here and put in whatever controller you have, and then you should be able to run a real test in the laboratory. For the computational drivers, I have a few slides on that. We have different computational drivers we can talk to, and so when we want to do that, if we want to use anything else than OpenSees, there's two ways to interface with other finite element software, as long as that other finite element software needs to have some user interface to it. So it needs to provide some functionality to define or basically program a user-defined element. And a lot of the commercial software, they do have that. So Abacus, Celestina, ANSYS, all these have these user interfaces. And so once you have that user interface in the finite element software, there's two ways to approach this, and I already pointed this out earlier. You can either implement a generic client element, which then that you only have to do that once because it's generic, or you implement an experimental element directly into that software, so which then means that you would have to redo this every time you test a different element. So if you have a beam column, you would do that. If you have then a truss, you will do that again. So really the generic client element, if you come along with a new software that we are not having an interface yet, the developer will have to program that interface. The ones that we already have, they're all available, and if you download the whole source code, not just the executables, so if you go on the developers and you get really the whole source code, then inside trunk, source, sim application client, inside that directory, you will find all the different generic client elements that allow you to talk to different finite element softwares. The ones that we already have are obviously, well, we have OpenSees, I showed you that. We have LS-DYNA, so we have a generic client element for LS-DYNA. We have Abacus. We have MATLAB, so if you want to talk or basically program your own finite element analysis for a simple problem directly in MATLAB, we have functionalities that allow you to talk, basically it's TCP/IP or UDP connections that allow you to connect MATLAB to OpenFresco. The same thing for Simulink. If you want to do your model in Simulink, we have a generic client element block that you can drop into your Simulink model, which then will talk to OpenFresco. And we also have an interface for UI SimCore, so that all exists. And as I said, we're developing currently an interface for ANSYS, so that should be available shortly. If you would like to get more information, you can download documentation about all these different things that I showed you today on the OpenFresco website. If you go to documentation, there's a lot of material available there from earlier workshops that we've performed in the past. There's material for all the different examples that are there. There's documentation. So go there and get your information. You can also get a peer report that talks a lot about different aspects of hybrid simulation and how, like, they all basically fed into the development of OpenFresco. So that one is available at the website there that you see at the peer website. So finally, so I'll give you summary and conclusion here. And so really what I showed you is that hybrid simulation inherently requires the close collaboration amongst experts from many different fields. And the different fields are structural, in the structural behavior field, the laboratory testing and control field, computational simulation is an important field that feeds into this, and also information technology. So with that, hybrid simulation fosters collaboration and communication among distant researchers in different laboratories. I showed you that OpenFresco, the environment-independent software framework for the development and deployment, provides an excellent platform for this collaboration. And that collaboration could be on-site at a local place, or it can be geographically distributed. And then also the modularity and transparency of the framework permits existing components to be modified and new components to be added without much dependence on other objects. So that's important too. And then finally, we have a very large library already available of hybrid simulation direct integration methods. Those are all available in OpenSees. We have a lot of different experimental elements in OpenFresco. We have experimental setups, controller models, we have event-driven solution strategies. They're all available in OpenFresco, and they are there for the researchers to choose from or to adapt from. So if you want to develop your own new stuff, you can go in, use what is there, and start adapting from that. It makes the whole development process easier and faster. So what we need from you guys, from all the users out there, are the feedback. So start running OpenFresco, run some examples, give us feedback on how well it works, what refinements that you would like to see, or what new features you would like to see. And if you're a developer and you develop your own stuff using OpenFresco, you add new elements, new control interfaces, whatever it is, hopefully you can send those contributions back so that the whole community can profit and start using also your development. So with that, we will extend the libraries that are available for the future. So with that, I will thank you a lot for your attention. And also, obviously, thanks a lot for sticking around. And I know I was a little bit long here, like 15 minutes over. But like I said at the very beginning of the presentation, I think it's important that I was able to show all this today, and that we can really could step through a whole example as well.